Hello everyone, welcome back to this video. The subject is cryptography. The subject code is 21EC642.
These are the vision and the mission of the department. In this module, we're going to discuss about groups, rings, and fields, finite fields of the form GF of P, prime numbers, Fermat's and Euler's theorem, discrete logarithm. The textbook to be referred is William Stallings, Cryptography and Network Security Principles in Practice, Pearson Education, 6th edition. So first we'll discuss about groups and rings. And before we start with this groups and rings, finite fields. Finite fields have become increasingly important in cryptography. A number of cryptographic algorithms rely heavily on properties of finite fields. The advanced encryption standard and elliptic curve cryptography, and also other examples that includes the message authentication code CMAC and the authenticated encryption scheme GCM. Here, with the sufficient background on the concepts of finite fields, we'll be able to understand the design of AES and other cryptographic algorithms that use finite fields. Because students unfamiliar with abstract algebra may find the concepts behind finite fields somewhat difficult to grasp. So we approach the topic in a way designed to enhance understanding. So fields are a subset of a larger class of algebraic structures called rings, which are in turn a subset of the larger class of groups. And both groups and rings can be further differentiated. Groups are defined by a simple set of properties and are easily understood. Each successive subset, which is called as a abelian group, ring, commutative ring, and so on, adds additional properties and is thus more complex. Finite fields are a subset of fields consisting of those fields with a finite number of elements. These are the class of fields that are found in cryptographic algorithms. With the concepts of fields in hand, we turn to a specific class of finite fields, namely those with p elements, where p is prime. Certain asymmetric cryptographic algorithms make use of such fields. A more important class of finite fields for cryptography comprises those with 2 n elements depicted as fields of the form GF of 2 n. These are used in a wide variety of cryptographic algorithms. However, before discussing all these fields, we need to analyze the topic of polynomial arithmetic. So with all of this preliminary work done, we are able at last to discuss about this finite fields of the form. So groups, rings, and fields are the fundamental elements of a branch of mathematics which is known as abstract algebra or modern algebra. In abstract algebra, we are concerned with sets on whose elements we can operate algebraically, so that we can combine two elements of the set in several ways to obtain a third element of the set. These operations are subject to specific rules which define the nature of the set. By convention, the notation for the two principal classes of operations on set elements is usually the same as the notation for addition and multiplication on ordinary numbers. It is important to note in abstract algebra that it's not limited to ordinary arithmetical operations. So this should become clear as we proceed. Groups, a group G, sometimes which is denoted by G dot. So here dot is an operator. It's a generic and can refer to addition, multiplication, or some other mathematical operation. It's a set of elements with a binary operation that is denoted by dot that associates to each ordered pair A, B of elements in G. An element A dot B in G such that the following axioms are obeyed. Axiom A1 is if A and B belong to G, then A dot B is also in G. Associative is A dot B dot C is equal to A dot B dot C for all A, B, C in G. A3 is identity element. There is an element E in G such that A dot E is equal to E dot A that gives A for all A in G. Inverse element. For each A in G, there is an element A bar in G such that A into A bar or A bar into A gives identity element E. Here let n denote a set of n distinct symbols for convenience. It is consisting of 1, 2 till n. A permutation of n distinct symbols is a 1-to-1 mapping from nn to nn. This defines Sn to be the set of all permutations of n distinct symbols. Each element of Sn is represented by a permutation of the integers pi in 1, 2 till n. So even A2, A3, A4, all axioms are obeyed here. So if a group has a finite number of elements, it is referred to as a finite group, and order of the group is equal to the number of elements in the group. Otherwise, the group is an infinite group. Your group is said to be abelian if it satisfies the additional condition, that is A5, that is commutativity of addition. A dot B is equal to B dot A for all A, B in G. The set of integers may be positive, negative, and 0. Under addition is an abelian group. The set of non-zero real numbers under multiplication is an abelian group. The set Sn from the preceding example is also a group, but not an abelian group for n greater than 2. When the group operation is addition, the identity element is 0. The inverse element of A is minus A, and subtraction is defined with the following rule, like A minus B can be written as A plus of minus B. Cyclic group. Exponentiation within a group is defined as a repeated application of the group operator, so that A cube can be written as A into A into A. Further, we can define A naught as E as the identity element, and A power minus n can be written as A inverse of n, where A is the inverse element of within the group. A group G is cyclic if every element of G is a power A power k of a fixed element A that belongs to G. The element A is said to generate the group G or to be a generator of G. So a cyclic group is always abelian and may be finite or infinite. The additive group of integers is an infinite cyclic group generated by the element 1. So powers are interpreted additively so that n is the nth power of 1. The next is rings. Ring is denoted as R. Sometimes it's also denoted by R plus into. It's a set of elements with two binary operations called addition and multiplication, such that for all A, B, C in R, the following axioms are obeyed. That is A1 to A5, and M1, M to M3 is applicable for multiplication. Closure under multiplication, associativity of multiplication, distributive laws. So a ring is a set in which we can do addition, subtraction, and multiplication without leaving the set. So with respect to addition and multiplication, the set of all n square matrices over the real numbers is a ring. So a ring is said to be commutative if it satisfies the commutativity of multiplication, that is AB is equal to BA for all AB in R. So S be the set of even integers, may be positive, negative, and 0. Under the usual operations of addition and multiplication, S is a commutative ring. The set of all n square matrices defined in the preceding example is not a commutative ring. The set Zn of integers, which consisting of 0, 1 till n minus 1, with the arithmetic operations, that is modulo n, is a commutative ring. Here are some of the properties of modular arithmetic for integers, that is commutative law, associative law, distributive law, identities, and additive inverse. So it's an integral domain, which is a commutative ring that obeys the following axiom, that is M5 and M6, multiplicative identity. There is an element 1 in R such that A1 into is equal to 1A gives A for all A in R, and no zero divisors. If AB in R and if AB is equal to 0, then either A is 0 or B is 0. So let S be the set of integers positive, negative, and 0 under the usual operations of addition and multiplication, and S is an integral domain. So this is for today's session. Thank you. Hello everyone. Welcome to the course on cryptography. In today's session, we'll discuss about prime numbers. So the main concern of number theory is the study of prime numbers. So in this section, we uh, study about this prime numbers concepts. An integer, that is p, okay, if it is greater than 1, is a prime number. If and only if its only divisors are plus or minus 1 and plus or minus p. So prime numbers play a critical role in number theory and in the techniques discussed in earlier chapters. So here this table plays an important role. Actually, it shows the primes that is less than 2000. So the way the primes are distributed here, note the number of primes in each range of 100 numbers. Any integer a that is greater than 1 can be factored in a unique way, as a can be written as a is equal to p1 to the power of a1 into p2 to the power of a2 into pt to the power of at. So here p1 less than p2 less than pt are prime numbers, and where each ai is a positive integer. This is known as the fundamental theorem of arithmetic. A proof can be found in this number theory. Here we can see we have a number 91 here. It is can be written as 7 into 13. Similarly, 3600 can be written as 2 power 4 into 3 square into 5 square. So it is useful to express this in another way. If p is the set of all prime numbers, then any positive integer a can be written uniquely in the following form. Like it can be written as a is equal to pi from p which belongs to p, that is p power ap. Here each ap is greater than or equal to 0. So in the right hand side is the product overall possible prime numbers p. So for any particular value of a, most of the exponents ap will be 0. The value of any given positive integer can be specified by simply listing all the non-zero exponents in the foregoing formulation. So the integer 12 is represented by a2 is equal to 2 and a3 is equal to 1. The integer 18 is represented by a2 is equal to 1, a3 is equal to 2. Integer 91 is represented by a7 is equal to 1, a13 is equal to 1. Multiplication of two numbers is equivalent to adding the corresponding exponents. Given a is equal to pi of, that is summation of, that is p power ap for all p belongs to the p. So this is equal to p power bp. So here defining k is equal to ab. And we know that integers can be expressed as the product of powers of primes. K is equal to p power kp. It follows that kp is equal to ap plus bp for all p belongs to p, capital P. So the k can be written as ab, product of a and b. If a is 12 and b is 18, then this can be written as 4 into 3. So 4 can be written as 2 square. 3 into 2 into 3 square as 216. Similarly k2, like 2 plus 1 is equal to 3. So here k3 is 1 plus 2 is equal to 3. Therefore 216 is equal to 2 cube into 3 cube, that is equal to 8 into 27. What does this mean in terms of the prime factors of A and B? To say that A divides B. Any integer of the form p power n can be divided only by an integer that is of a lesser or equal power of the same prime number. Pj with j less than or equal to n. Thus we can say the following, that if b by a, then if b is divided by a, then ap is less than or equal to bp for all p. A is equal to 12 if b is equal to 36, then 36 by 12. So 12 can be written as 2 square into 3, 36 can be written as 2 square into 3 square. So here a2 is 2, which is equals to b2, a3 is 1, and this is less than or equal to 2, that is equal to b3. Thus the inequality ap less than or equal to bp is satisfied for all prime numbers. So here a relationship which always holds is if k is equal to GCD, greatest common divisor of a comma b, then kp is equal to minimum of ap comma bp for all p. And determining the prime factors of a large number is no easy task. So the preceding relation it will not directly lead to a practical method of calculating the greatest common divisor. Thank you.